Well, this is a tutorial on how to use graphical analysis. Now, graphical analysis is already built into Logger Pro, and so you can click on either the graphical analysis or the Logger Pro icon and access graphical analysis. So click on the graphical analysis icon or the Logger Pro icon, bring that up, and what we see is a table, XY table, and then a plot or an empty plot. And we're going to put some data in, I want to go back maybe a little bit later and talk about some other features, but let's just say we want to graph something that's linearly related. That is, y is linearly related to x, y being the dependent variable and x being the independent variable. Sometimes x is time, quite often x is time, and y is whatever the quantity is you want to look at and see how it depends on time, for instance. So let's say we're taking a brisk walk and we're walking at 2 meters per second. So every second you walk, you move 2 meters. So let's make a graph of that, of your first several meters. So the y-axis is going to be distance. In fact, we might want to click on the y-axis on top and double click on that, and you can type in distance, and units would be meters, of course, and then we can click on the x-axis, and that would be time in seconds. Okay, so we have our axes labeled, and that's probably one of the first things you want to do. And if you want to label the graph itself, just click any place on the graph, double click on that, and you can put in a title such as distance versus time. Okay, so we're ready to go, and so let's make up some data. I'm going to make up some data that says we walk at about 2 meters per second, which is a brisk walk, it's a little bit less than 5 feet per second. So let's start out at 0 in distance and 0 in time, assuming we start out with a stopwatch or something that's set at 0, and we start out with a measuring device that starts at 0. Okay, we're going to walk for 1 second, and we're going to go 2 meters. Let's say it's 2.0 meters. This is an experiment, so it's not going to be exact, which is the point of graphing things. So let's say it's exactly 2 meters. We'll just leave it at 2 then. And we're going to walk another second. Second number 2 then would be 3.9 meters. Maybe we stumble on a stone or something. And then the third second, we're going to walk 5.9 meters. And the fourth second, and that's probably enough to illustrate, we're going to walk 7.8 meters. Okay, so there's our data set, and we've got 5 positions, and the computer automatically, usually, fills up your screen with your data. And if it doesn't do that, we want to go up to the blue A in the icon list and click on that, which is the auto scale button. And now the auto scale button really does fill up the entire screen with your data. So if you want to do that, hit the auto scale button and fill up your screen with the data. So we have some points here that look like they're pretty much in a straight line, and we want to see if they indeed are linearly related, and you would think they should be. So if we go up to the icon list and go to the second one from the right, that's the linear fit. If you park on that long enough, it'll tell you that you're in the right place, linear fit. If you click on that or double click on that, then you get a nice straight line, which is what's called the best fit straight line, the linear regression fit straight line to your data. And of course, because these are real data, well, I mean, we're assuming they're real data, the points don't all fit on the line. By the way, you see those little red circles with the dots on them. The dots, of course, are the data points, and the circles kind of indicate where the data are. And sometimes they're on the line, which means you can't see the dot. So it's nice to put a little circle around it. Those are called point protectors. And we will then be able to see where our data are, whether they're on the line or not. So they're pretty much on the line, because this is, if you move at a constant speed, this is a pretty much linear graph if you walk at a constant speed. So you look at the box there, the linear fit, you see that the slope, which is 1.9 1.950. That's about what I expect. As if I'm walking about 2 meters per second, every second I'm going to walk 2 more meters. And that's the linear relationship we're looking at. Now, all relationships are not linear, but sometimes we like to make them linear, like in the first measurements experiment, where we want to plot a period versus the square root of length for mathematical reasons we'll talk about later. And so most of our graphs, because when you plot a straight line, you know what a straight line looks like, and you know how well your data fit that straight line. It's just automatic understanding of how good a fit your data are to the line that fits them best. And these fit pretty well, and so not perfectly. And so we see the slope is just a little under 2, which of course makes sense because I only walked 7.8 meters in 4 seconds instead of 8.0 meters in 4 seconds. So I'm expecting a little number, a little bit less than 2. Now, the intercept is irrelevant. In this particular case, we started out at 0, and it shows that it's the y-intercept is 0.02, which means the best fit straight line doesn't start out at quite 0. But we're not interested in that. We're interested in the slope. And why is that? Because distance traveled divided by time elapsed, distance divided by time, or displacement divided by time, is the definition of velocity. So that slope is my velocity, which is, of course, 1.95 meters per second, to be more specific. So the slope is what we are looking for. How fast am I walking? On the average, 1.95 meters per second. And if we double-click on that little box, it tells us something even more interesting. If we select Show Uncertainty on the second box and hit the OK button, we will see a second box, or we will see data put in either a second box or in that box, giving the error in your values, which is really what we're looking for here. Not just the fact that it's a pretty much linear relationship, but how close to perfectly linear is it? And the plus or minus on the slope, which is the velocity, gives you a plus or minus 0.01, which basically means, or 0.1010, a bunch of zeros, which means if we look at the slope 1.950, that's accurate to plus or minus 0.010 meters per second, which is 0.5%, basically. So that's pretty accurate. Also, if you want to change, if you go back and click on that box again, you want to change the number of decimal points you display, you can do that. If you do a really accurate experiment and you want to analyze it to 5 significant figures, then we go to the second box and also indicate by changing the 4 to 5 to produce 5 significant figures. And let's see what we get. So we get 1.9500 plus or minus 0.01, a bunch of zeros. So that didn't really tell us any more than we really knew before. Sometimes the numbers of the plus or minus value are a little bit different and tells you something. But in our experiments, let's face it, and we've talked about that, or we will talk about that in the video, we generally have 2, maybe 3 significant figures accuracy. So this may be kind of a moot point. But you can change the number of significant figures displayed in both the values and the answers, or the number of decimal places, whichever you prefer. Okay, so that's our result, and that's how to fill the screen with your data points by using the A symbol, the auto scale symbol. And now if we want to go to print it, we just have to go back to the File menu, and there's a couple options, which are, and the option I recommend is not the print option, because the print option prints the entire screen which you're looking at, and that includes your data, which you already have probably in a table someplace, a data table in your results. So we want to fill up the entire screen with your graph, and therefore we go to the print graph option, and then when you print it out, you'll get a full page display on landscape style of the entire graph, filling the page. which is a little bit more gratifying, I think. So you can do the print button, but the print graph button gives you just the graph and not the data also. So sometimes your little bitty data box is full of little bitty numbers, and if you want to make this more easily seen, you double click on that box and you go to Appearance, and you can change the appearance to a larger font size, say 16, 20, whatever you want, and then the box gets bigger. Yes, and that's very visible. Even I can see that. Okay, at some point, at several points in the upcoming 25 or so labs that you're going to do, you may want to plot something that actually is not linearly related. We can do this for even sine functions or cosine functions, which you'll see next semester. But let's say this is a graphical plot. Now, if you plot, if you have an accelerated motion, which you will be talking about in Chapter 2, what that means is if you have an acceleration, you don't go the same distance every second. You go farther and farther every second that elapses. And so let's just say that that's a squared relationship, which it actually is a parabolic relationship. So here's where you want to fit your data to a parabolic curve. So let's start out with 0, 0 again, 0 distance, 0 time. And the first time we're going to be will be 1 second, and the distance can be 1 meter also, or one unit, whatever. The second time would be 2 seconds, and then the distance traveled would be the square of that, which would be, well, let's say not quite 4, maybe 3.9 or something like that. And the third point would be 3 seconds, and maybe 9.2 instead of 9.0 seconds. So this is data after all. And so let's try one more, 4 seconds and 15.7 whatever units that we're talking about. Okay, now again, the data is going to fit a curved, a parabolic plot, so we go to the Analyze section and go down to the Curve Fit section, and there's our graph. And we want to fit it to a curve. Now this is a parabolic curve, so if you look around the parabolic or quadratic curve, we have an option here of quadratic. Okay, so that's a quadratic fit. Let's try that, parabolic fit. And so try fit, and yes, it is very parabolic fit. So in your free fall experiment you're going to do in a couple weeks or a week or two, you're going to plot distance versus time elapsed for an accelerated quantity, such as the distance something falls and under the influence of gravity, gravitational acceleration. So it's going to look like this, and you're going to get a graph that looks pretty much like this. You're probably going to get about 15 or 16 points instead of a few points like this. And again, if you double click on the box, you really don't have to double click on the box because it's already got the error in the various quantities here. And I'm not going to get into the weeds here, but so this is the same procedure, and you get the same information, and you can change the number of significant figures, you can make it bigger and so forth, and then you can print it out using the print graph option, and you've got a nice graph of position versus time for an accelerated object such as a falling body, which you'll see in a week or two. Okay.